Let us continue with, with our lecture on diffraction. So before going further, I would like to give you a quick recap of whatever we have done in last few lectures. So in the last lecture, we have done Fraunhofer diffraction due to single slit, in which we have considered the width of the slit, and we have seen that how our intensity modifies when we take the width of the slit into account. So we have seen that our slit was divided into n equal parts with phi as a phase difference between two consecutive parts. Then we have taken the resultant of those n parts as n waves, and we saw that we got the resultant as R is equal to A sin alpha by alpha, where alpha is equal to pi by lambda E sin theta or n phi by 2. And from the resultant amplitude, we found out the resultant intensity as A square sin square alpha by alpha square. Then we examined the positions of maxima and minima by using this relation. We found out that at what positions or what values of alpha we are getting maximum intensity and the minimum intensity. So we saw that for alpha is equal to 0, we got maximum intensity as A square, that is this point. And then for minimum intensity, we checked that where we are getting the numerator as 0, that is sin alpha is equal to 0, and we got that for alpha is equal to m pi. And these are these points for minima. In order to find other maxima, we have used the general equation of di by of maxima and minima as di by d alpha is equal to 0. And we got the intersection point of two equations, tan alpha is equal to alpha. By finding out the intersection points of these two equations, we found the points as 3 pi by 2, 5 by 2, and so on for the secondary maximas. Also, we have observed that the intensity of the secondary maximas is continuously decreased as we increase the value of alpha. So this was all about the intensity pattern, or how intensity modifies when we take into account the width of the slit. So we have seen that in Young's experiment, we took two narrow slits separated by some distance, and we got the intensity pattern like this. Then we have studied the effect of the slit width, and we got the intensity pattern like this. Now next, what we can do? The next thing which we can learn is that when the slit width becomes comparable to the distance between the two slits, that's what we are going to do next. So we have increased the width of the slit until it becomes comparable to the distance between them. So in order to do that, I will be using many slits instead of one slit, and try to see how intensity modifies when we take n slits. We also call this as grating. So how do I define grating? Any arrangement which is made up of parallel equidistant slits of the same width is termed as grating. So basically we are trying to study the intensity modification, or how intensity modifies when we take grating. So let us do that. Let us take a grating which consists of n slits of equal width and so on. And then I'll be taking a screen and a lens, and then let us take the slit width as E and the opaque space between two slits as B. So then one slit, one opaque space, again slit, opaque space. So this E plus B would be repeated n times. This is known as grating element. E plus B is called as grating element because it repeats to give me full grating. Then from the left, I shine light on this of wavelength lambda and try to observe the pattern on the screen. Let me call this as S1, S2, the endpoints of this grating element, because after this it will repeat. So if I study the pattern due to 1, then I can just take the superposition of n such patterns. That's what we are going to do. So from the one grating element, I take 2 rays from the endpoint which are being diffracted at angle theta, and they meet at P. So now, according to Fraunhofer and all these patterns we have already studied. So we have seen here we have a slit of width E, which again is made up of many points or secondary wavelets by Huygens principle. And I know that all the secondary wavelets in a single slit, they combine to give me a single wave of amplitude A sine alpha by alpha, where alpha is equal to pi by lambda E sine theta. How do I get this? I can get this by dropping a perpendicular on this. So if this is theta, this is again theta, I will get the part difference as E sine theta, and the phase difference is 2 pi by lambda E sine theta. So then I have defined my phase difference n phi by 2 as alpha. So from the single slit, all the n waves, all the waves, they combine. They're not n waves, there are infinite number of waves, and they all combine to give me, or I can take that as equivalent to a single wave of amplitude A sine alpha by alpha. Now, so, and such kind of, I have n slits. So there are such n slits, and from each slit I will get n diffracted parallel rays. So now what is left in order to find the resultant intensity on P? From every slit I have one wave whose amplitude is A sine alpha by alpha. I have n such waves. So what will I do? I will just take the superposition of these n waves, and I'll get the resultant intensity. That also I have done earlier. I know the resultant of n waves if I know the phase difference between two. So what do I do? Once again I draw the pattern. Bigger diagram I'll draw. So here I have a screen. They meet here. I draw a neat diagram. So here theta, S1, S2, this is E, and this is B, the opaque space. Here I know P. Now I drop a perpendicular onto here. This angle is again theta, that we have discussed earlier. Let me denote this by K. Now there are n diffracted parallel rays, one from each slit whose amplitude is A sine alpha by alpha. So basically now I have to find these n waves and just take the superposition. But before doing that, using the resultant formula, I need to find the phase difference between these two waves. The path difference, so we need to superimpose these n waves. The path difference between S1p and S2p, this is equal to E plus B sine theta, that is equal to S2k, that you can see from the figure. E plus B sine theta. The phase difference would be 2 pi by lambda E plus B sine theta. Let me call this as 2 beta. See. Now what we have to do, we have to just use the superposition of these two waves. Then let us find the resultant of these capital N waves. We would continue in the next lecture.